Hi, I'm Andy Zimmerman. I'm the Chief Technology Officer here at Grace Technologies. And today I'm just going to spend some time talking about a topic that's been really influential, both to what we're doing here at Grace, but also to what the world has been doing in terms of leveraging artificial intelligence for monitoring industrial equipment. Specifically today, we'll get around to a bunch of different topics, but the focus will be on explainable artificial intelligence for driving trustworthiness in vibration-based asset management. So my background here from an academic perspective, I come out of the University of Michigan where I did my master's and PhD work. In that era, I was focused heavily on civil engineering as well as computer science. And the work that I did there really drove towards building low-cost, low-power wireless sensors that could be used to monitor complex civil infrastructure like bridges, buildings, ships, wind turbines, and what have you. Out of that background, I formed a company called Civionics, which took that technology into the commercial marketplace where we really focused on structural health monitoring and later on true predictive maintenance or industrial Internet of Things applications. So that has since migrated into Perceive and Grace Technologies, and that's kind of the ecosystem out of which I'm presenting to you today. Before I get going, I also want to just throw a shout out to my colleague, Dr. Chao Hu, formerly with Iowa State University, currently at the University of Connecticut. Chao and I have worked on a number of research grants over the last 5 years that have really been designed at building machine learning and artificial intelligence-based technologies that couple with the Internet of Things and predictive maintenance work that we do here at Grace. I mean, a lot of the content that I'm bringing to you today comes out of that collaboration. So I wanted to make sure up front that we recognize his contributions to this work. So the presentation today will be fairly simple in format. We'll talk a little bit about industrial maintenance from a historical perspective, move on to talk about why vibration in particular is important to industrial maintenance, then talk specifically about how the industrial Internet of Things has impacted that ecosystem, and then drive it home with opportunities for artificial intelligence in the predictive maintenance space and why explainable AI is important for driving trustworthiness in AI-driven predictive maintenance. So to start with, let's just talk about maintenance as a general concept. How do we as maintenance and reliability engineers keep factories running? That's a pretty simple equation, right? We try to find when things are going wrong, and then we try to fix those problems as they occur. And lastly, we try to hopefully keep those problems from occurring again, right? That's the formula for success. But really what's been happening over the last several decades is a focus on how can we take that simple formula and make it better? Can we identify problems earlier? Can we fix problems faster? Can we eliminate downtime entirely? And this kind of spectrum of approaches from corrective maintenance all the way up to modern predictive maintenance have taken hold in an effort to kind of achieve these three goals. So let me just walk you through each of these approaches one at a time, and then we'll get into the brunt of the presentation on the back of that. But I want to make sure that we're, from a terminology perspective, fairly aligned. So to start with, the very most basic type of maintenance is going to be corrective maintenance, where we're basically going to a problem that we know exists and we're fixing it once a failure has occurred, right? This is great when we have equipment failure that doesn't really significantly affect anything in our industrial ecosystem. And we typically use this on non-critical assets that have a really low cost of repair. So for example, I'm never going to recommend that you throw an IoT or a predictive maintenance system on just a standard light bulb. If we want to get to a slightly more, there's some advantages to this particular approach. It's really cheap to implement because you don't have to do anything until the thing fails, and you don't need to plan for that maintenance. You're just reacting as things happen. However, because of those two advantages, we actually oftentimes lead to long-term costs that are higher because we have unplanned downtime. We also have urgent repairs, which can drive up labor costs. I mean, we potentially drive secondary damage into our equipment because we let it run in the damaged state for too long. Additionally, this type of maintenance approach is hard to schedule, and it often requires, labor to be brought in on kind of a firefighting type schedule. So this really drove the community to build out preventative maintenance approaches that would come in with routine inspections and help service equipment regularly in order to hopefully prevent failures before they occurred. Right? We use this typically on assets that have failure modes that we understand pretty well and that we can anticipate with some degree of accuracy. And this makes it ideal for critical assets where that failure can lead to significant downtime. But we do have to understand how those assets are going to fail. So changing oil in any sort of system that requires lubrication or oil changes, that's an important preventative maintenance action that we do on a regular cadence, right? This particular approach has several advantages. It can reduce the likelihood of that unplanned downtime. That's why we do it. It can extend our equipment lifetime because we're regularly maintaining it. And we can really predictably budget for preventative maintenance kind of actions like lubrication. However, this often leads to unnecessary maintenance. If we're over-maintaining an asset by, for example, lubricating it too frequently, that can happen in this particular type of approach because we're just maintaining on a cycle. It does require a pretty good understanding of equipment in order to effectually deploy, and we typically rely on a manufacturer to tell us how frequently we need to maintain a particular asset in a particular way. And ultimately, this does require a significant amount of planning and labor to execute. So if we move above and beyond from a sophistication perspective, the preventative maintenance approach, we start to see condition-based monitoring or condition-based maintenance techniques emerge, right? And this is where we're drawing on sensors to monitor equipment that we're interested in maintaining, and then using that sensor data during normal operation to detect issues that hopefully are indicative of problems before those failures fully manifest. We typically deploy these kind of condition monitoring approaches on complex or critical machinery that have regular operating conditions and pretty well-known failure modes. This is especially effective when downtime can result in significant costs, right? So an example of how this is done frequently is we take a vibration sensor and we have ISO standards that we know are damaging to the equipment that we're monitoring. And when that vibration sensor trips that threshold, we issue a maintenance work order, right? So this has many advantages in that it really does optimally minimize downtime in many cases. It helps us optimize our scheduling because we know a lot of times before something catches on fire, we know that there's a problem. And it does increase the equipment lifespan because we catch problems earlier in a lot of cases than we would with just a run to failure approach. And oftentimes it increases the lifespan because we're not maintaining as frequently as we would with a preventative maintenance or routine-based maintenance approach. However, this does require us to invest in specialized tools and technology. It requires expertise in how to collect data and process that information and interpret it correctly. And over time, the systems that we put in place to monitor our critical equipment also require maintenance, and that can cause problems in many cases. So the last kind of approach to maintenance is what we call predictive maintenance. A lot of times that term is used instead of condition-based maintenance for multiple things. But what we're talking about here is really maintenance activities that leverage statistical techniques and artificial intelligence or machine learning kind of contexts in order to analyze current and historical data that we're capturing from sensors, right, in order to predict future outcomes for the piece of equipment that we're monitoring. This is used for generally critical equipment, just like the condition-based monitoring approach, with high downtime costs, right? We're going to put a lot of investment into the equipment, and as a result, we expect to get a high degree of certainty in terms of predicting failure before it occurs. Examples of how this is used in industry is to establish standard machine behavior and then issue alerts if we have anomalous behavior or if we deviate from the norm. Excuse me. We also use predictive kind of techniques in order to estimate remaining useful life of machinery or the components therein based on that data that we've collected historically. This really does allow us the maximum amount of time to schedule maintenance because we know in advance when something's going to go wrong. It does minimize the potential for us to wear and tear unnecessarily equipment that is already degraded. And it really allows us to understand better what's happened in the past in order to kind of predict and understand what might happen to that equipment in the future. But it's expensive, right? It requires high quality, high volume amounts of data that need to be captured in order to work effectively. It does require expertise in data analysis, data interpretation, just general data science, and it creates some unique cybersecurity and data privacy risks. And the one piece, and I'll talk about this a lot later, is that the lack of explainability, a lot of times when we're predicting something, can lead to a lack of trust in this sort of predictive system for giving insight into how to maintain a given asset. So the second part of this talk, I'm going to pivot a little bit and talk specifically about vibration. And it's important, I got to lay this foundation too before we talk about how explainable artificial intelligence can impact vibration-based condition monitoring or vibration-based predictive maintenance. So vibration is important in all sorts of predictive maintenance, or not just predictive maintenance, but maintenance, industrial maintenance activities, because it does allow us to detect issues earlier in the process. And we usually use this sort of a plot to describe this, right? So on the bottom, we have the amount of time that we have before a fire or a catastrophic failure occurs of a piece of equipment. And the top is kind of how much resistance or resilience to failure we have in place. So a lot of times if we're running to failure, we don't know what's happened before the failure occurs, right? That's that run to failure example I talked about earlier. If we're doing any sort of paying attention, some sort of route-based visual inspection, a lot of times we do have some early insight into this failure about to occur because we see some smoke or something's making noise. It's humanly detectable that there's something going wrong in the asset that we're trying to monitor. If we have certain sensors in place, current and temperature generally, those can tell us, hey, this piece of equipment is experiencing some frictional losses, which are generally indicative of something going wrong inside that equipment, and we might want to do something about it. And those sensors typically start to alarm before a human knows or can tell just from a route-based inspection that something's wrong. But when we get up to the kind of high end of this curve, we start talking about vibration. Vibration gives us the earliest possible indication that something is up. And when a vibration threshold trips, it's generally a very early indication that we should begin to schedule maintenance on the rotating asset that we're interested in. Now at the top end of this, right, the pie in the sky here is that we can bring in all of these data trends and give a true predictive opinion of when these issues, the vibration, the temperature, the current, when those issues are going to start to hit the thresholds at which we'd be alarming. And that allows a maintenance team to schedule in advance when they're going to do their maintenance to try to prevent the equipment from decaying to the point where it might cause long-term problems. And that has a lot of return on investment opportunities because the longer you wait to maintain that asset, likely it is more expensive to repair or replace that particular asset. If you get to it early, a lot of times it's just a matter of performing the maintenance action and allowing the equipment to continue to run. All right, so what can we do with vibration-based data or vibration-based condition monitoring? We can detect, trend, classify long-term degradation in a number of different systems. This degradation can look like misalignment, unbalance, mechanical looseness. We can detect bearing issues, gearbox issues. A whole slew of different maintenance-related problems can be picked up early on using vibration analysis. And we typically, when we're talking about vibration analysis, we're talking about rotating equipment. So things like motors, pumps, compressors, fans, etc. Anything that has a shaft and that spins. What we can also do with vibration is detect and classify degradation that's more structural in nature. So things like cracking or material hardening or softening. And we can deploy these in applications like cranes or footing supports, like structural supports, or equipment that's subject to kind of impulse loads like AGVs, stamping presses, that sort of thing. Now, typically everything I'm going to talk about today is more focused on those rotating type of applications, but just be aware that vibration can be leveraged outside of the rotating context. So, all right, the next few slides here are what I call my kind of very basic vibration 101 primer. So I apologize if you've kind of seen this before or you come from a vibration background. It's going to be pretty simplistic. But I do need to set that stage in order to really talk about how AI can come in on top of this type of technology. So when we have a piece of rotating equipment, the health of that equipment really is all going to start with what the shaft is doing. If everything's healthy, this pillow block bearing, and I'm hoping you can see it spin here in this slide, it shouldn't move at all, right? That shaft should spin nice and smoothly inside that bearing, no vibration at all. If I add a defect to this, in this case, I've got a small unbalance. What we're going to see is there's going to be a displacement, right? If you put your hand on that, you're going to start to feel that particular bearing move a little bit. And that means it begins to displace. We talk about displacement in terms of inches, amount of actual physical displacement. We talk about the change of displacement as velocity, which we're typically putting in a unit of inches per second, how fast it's moving. And then we talk about the change of velocity, or the acceleration of that pillow block bearing is typically measured in either units of g, which is proportional to gravity, or inches per second squared. So when I talk about vibration from here on out, I could be referring to any of these quantities: the displacement, the velocity, or the acceleration that's being experienced by a rotating asset. All right, so how do we monitor that in a piece of equipment? I'm not going to spend a lot of time on this, but if you wanted to go out and monitor displacement directly, you'd typically be using something like a potentiometer, linear voltage displacement transducer, some non-contact optical devices. But these are often really difficult to install. They're expensive. They require a super stable reference where you can mount the equipment to something that's not moving. Just generally not advised for doing vibration-based monitoring of standard run-of-the-mill rotating equipment. Velocity sensors that are going to measure velocity directly, things like piezoelectrics, LVTs, geophones, these are generally expensive. They're hard to miniaturize. You tend to have a relatively large sensor that gives you velocity output. And in general, these also are not used in the field. So what we typically see in almost all applications is some sort of accelerometer. This is a device that directly measures acceleration, typically either MEMS, microelectrical mechanical, or piezoelectric in nature. I'm not going to go into the differentiation there, but these accelerometers can be miniaturized. You can make them incredibly small, in some cases, millimeters of size in an integrated circuit. They're easy to miniaturize, like I said, and they're also inexpensive, right? So we can deploy them in large numbers without a lot of capital being expended. And then from there, we can take data that we capture from the acceleration domain and we can numerically convert it back into velocity or displacement with minimal amount of error. So, all right, so how does this look like in practice? Well, we have a defect, right? In this case, an unbalance. It's causing vibration. We plop an accelerometer, in this case, on the top of the bearing. It's going to capture acceleration and convert that to voltage. That voltage is going to go to some computing system that's going to digitize that voltage for a microprocessor. And that processor then is going to analyze that data, display data, issue alerts to the maintenance team, et cetera. That, at a high level, that's how one of these systems works. So when we start talking about that data, now that it's hit that computer system, the first question that you might ask is like, well, okay, does the amplitude matter? And generally everyone understands, yes, amplitude does matter. It's intuitive that if you have a system that's vibrating more, it's going to be more damaging, right? So if I increase the size of the defect in the system, I'm going to see an increased amplitude of the acceleration output. And as a result, there is going to be a direct tie between the size of the defect and the amount of vibration that we're seeing. However, I want to make it super clear that severity of a defect is also dependent on frequency, right? And what I mean by that is that as we look at two similar bearings that are experiencing an identical displacement, okay, the one on the left of this screen is experiencing low frequency vibration, and the one on the right is 10 times higher in terms of the vibration. It's both the exact same amount of displacement. If I let these two things go, one of these two pillow block bearings looks a lot worse than the other, right? And it's true. The one on the right here that has the higher frequency is experiencing more damage than the one on the left, right? So high displacement is more damaging at high frequencies, okay? If we flip that to the other side of that spectrum and talk about acceleration, so these two bearings that you see here are experiencing the same level of acceleration, but 10 times different frequency of vibration, right? Again, I'll set these going. All right, well, if I look at these two things and they're my washing machine, for example, the one on the right here, this high frequency vibration, that's probably okay. But if I see my washing machine do the thing on the left, I'm going to be super concerned because of the amount of displacement that it's drawing in that low frequency acceleration. So contrary to when we're monitoring displacement, acceleration is more damaging at low frequency. Okay. So what we typically end up doing is we monitor velocity. And I'll show you the reason for that here. We got a similar example where we've got two bearings experiencing the same amount of velocity, but at a 10 times different frequency. And when you look at these two bearings vibrating, they look, it's hard to tell which one is more, it has the higher potential for damage, right? And that's because high velocity is generally equally damaging regardless of the frequency at which that velocity is being recorded. And this plays out in a lot of ways. What I'm showing you here is the ISO standard table for vibration severity in rotating equipment. And I'm not going to talk about this in any sort of detail, but if you kind of look at this is a velocity-based chart. So if you draw a horizontal line at right about 0.3 inches per second, you see that anything above that is going to register as red or as damaging. Right? And if you draw another line at right around 0.1 inches per second, everything below that is going to register as healthy, right? And so the idea here is just by knowing these kind of rule of thumb values, doesn't matter what kind of equipment it is, how big it is, we can generally use velocity to know roughly how damaged a piece of equipment is going to be based on the vibration that we're reading from it. And this is one of the reasons why vibration is so impactful in condition monitoring. So last little bit in my primer here is going to talk a little bit more about frequency. Second reason why frequency matters is because it's indicative of the type of defect that that is occurring in our rotating equipment. At low frequencies, if we start to see low frequency output, that's typically so this subsynchronous band here that I'm talking about is less than 1 times the run speed of the motor. That typically is indicative of things like mechanical looseness or isolation. Synchronous faults that occur right about the same speed as that shaft turning, in fact, exactly the same speed as the shaft turning, that will manifest defects like unbalance, eccentricity, gear tooth problems, that sort of thing. And then you get into harmonics, where other problems like alignment or blade problems, gearbox issues start to manifest. And then bearings, belts, electrical problems will typically come out in non-synchronous or non-integer multiples of the shaft speed. And I'll give you an example of this on the next couple of slides. So to put this all together, what this really looks like is if I have a bearing here that's driving a pulley to this fan, or the fan is on the shaft, kind of doesn't really matter. This is overly simplified. And I've got a defect in both the fan and the shaft. I'm going to get kind of two different output waves in the acceleration domain. We're going to get a slow frequency sine wave from that unbalanced defect, and I'm going to get a high frequency sine wave from the blade pass problem that we have, a chipped blade or what have you. Now, I am overly simplifying here. So for those of you that understand your vibration dynamics, just note that I'm simplifying this down a bit. But when you combine these two defects, what you end up with is a combination in the acceleration domain, a waveform that looks like what you see in the bottom left of this figure. And when we take that from one of our sensors and push it through our processing approach, the first thing we're going to do is we're going to look at it in terms of its velocity component. So we'll take it via numerical integration from acceleration to velocity, and then we'll run a discrete Fourier transform, which is going to allow us to position it not as a time history waveform, but as a frequency spectrum. And again, in this idealized case that I've drawn up here, which is overly simplified, we see these nice, beautiful peaks, one related to the defect caused by the unbalance, and one related to the blade pass issue that we're seeing on the fan blades. Okay, so this concept plays out in much the same way as what we talk about when we're looking at graphic equalization for a stereo. So if you've seen a stereo with a graphic EQ on it, it looks like this, right? And at the left side of this, you see your bass, and on the right side, you see your treble, and those sound bands from a frequencies perspective are broken down between that kind of low end and that high end. So we do the same thing when we're monitoring rotating equipment. We break down that vibration signal and look at the low frequency components, which are our subsynchronous band here, and we look all the way up to our high frequency components. And depending on where we see levels populate themselves in that spectrum, we can see a tremendous number of different problems manifest, from unbalance and eccentricity, all the way through the alignment and looseness problems up to the more high frequency issues like fluting or bearing gearbox problems. So this, when we're talking about vibration monitoring, this is the second reason why it's so impactful. A, it gives early indication of problems, and B, it lets us identify and classify with some degree of certainty what the actual problems are that we're seeing. So here's an example that comes from some actual data from a defect experienced in the field. When you're looking at this plot, what you're seeing is the frequency related output of a vibration sensor going through time, kind of going back into this image. And you can see at the beginning of the monitoring cycle, there's very little, nothing happening towards the front of the screen. As you move back, you start to see these kind of large spikes occur, and those spikes get bigger and bigger over time, right? So we're gonna see a couple of things here. If I look at this just at a high level, over time, I'm gonna be like, man, I'm starting to see more and more vibration, right? So that means, just by itself, that means probably there's something bad happening. Secondly, I'm gonna be able to isolate that there's a frequency band here kind of between 3.2 and 12.2 times the shaft speed. We probably know, given that most of this behavior is happening there, this is probably a bearing related issue. And then if I really hyper focus on specific bands, in this case, we're focused on multiples of this 3.2, which in this case, because of the dimensions of the bearing that we're using, that happens to be the outer race frequency for that given bearing. We know with a high degree of certainty that this particular issue is a ball pass frequency problem on the outer race of this bearing. So just from the vibration data that we've captured, we're able to detect a problem, kind of trend its increase in severity, and then identify roughly what that problem is in the end. So next section of this, now that we've established a baseline for what maintenance has looked like historically and how vibration plays into this ecosystem, is to talk just really quickly about how the Internet of Things has emerged to really amplify the benefit that we can get from vibration-based condition monitoring. So in recent years, IoT technologies have emerged, as I'm sure we're all familiar with, and these have really revolutionized the way that we can do vibration monitoring. They brought about low-cost sensors that can be integrated with low-cost hardware, right? So usually a wireless device that then get integrated with low-cost web-based software, right? We're taking data in a wireless device and we're pushing it up to the cloud, and all of this can be deployed on a critical asset for a relatively low cost. Additionally, because we're using battery-powered wireless communication, we can deploy these things pretty easily in the factory, right? You take a magnetic wireless vibration sensor and you deploy it on your rotating piece of equipment, and you're ready to rock and roll. That's the extent of the deployment strategy. All right. So if we look at why this wireless approach has been so impactful, first let's talk about the pros and cons to deploying wired accelerometers to do vibration monitoring. The really biggest negative to a wired accelerometer is that it's expensive. You have to buy a sensor, you've got to buy cable, you've got to buy conduit, you have to buy the people to install it, and in general, monitoring one point with a wired accelerometer can end up being very, very expensive, and sometimes it's infeasible. It loses its value because of how expensive the install is. On the flip side of that, wired acceleration monitoring is really reliable. You've got a sensor in place. You can bring that data back to a server. You can do whatever you want with the data. It's always available. You've got nearly unlimited bandwidth. The power's not a problem. These are all positive things. When wireless sensors emerged, the reason why they've been so impactful is because they're inexpensive to install, right? It's a low-cost sensor. It can be magnetically deployed. It's really, it reduces to almost zero relative to the wired case, the cost of monitoring a system with vibration sensors. However, we also run into problems related to communication, bandwidth. We only have so much wireless bandwidth we can use. And because of the battery powered requirement, you got to change batteries, which is never like the most fun thing to do. So one of the things that has emerged as coupled with this emergence of IoT technologies for monitoring vibration is a increased focus on embedded data processing. And this really comes out of the fact that wirelessly transmitting raw data, vibration data specifically, isn't usually feasible. In general, when we do a vibration analysis, we're taking tens of thousands of data points and we're coupling them into a collection cycle to do analysis on. And when we have this and we've got maybe hundreds or thousands of these wireless nodes in a facility, the wireless bandwidth just doesn't support that sort of throughput. And a lot of times our batteries don't last very long if we're trying to send all that data at once. So what typically happens in many of these wireless vibration platforms is we focus on embedded data processing. We capture that data in the sensor itself, and then we process it there as well. And that allows these devices to work in a battery-powered sense 24/7. So we can do all that banded frequency analysis that I showed you earlier and damage predictions all down in one sensor. And that allows us to then, when we communicate up to the cloud, we're only sending like maybe less than 100 processed data points instead of tens of thousands of raw acceleration values up to the cloud. And that leads to increased bandwidth, more sensors deployable in a facility, and also a longer battery life. So I'll take this quick second to talk about the Grace ecosystem. Now, this is very similar to a lot of the competitive approaches you'll see. When we go to market with our condition monitoring system, we typically start with the sensor on the left. Obviously, we've talked about our wireless vibration sensors. We also have a hotspot monitor and other wireless panel mount capabilities in play. Those devices will transmit information to one of our gateways, which can either be cloud hosted, so that's your standard IoT deployment. Data goes from wireless sensor to gateway and then up to our cloud, or we can deploy what we call a control gate, which is going to take that same data and make it available to a PLC or a SCADA, something else on your industrial control system. In the middle here, we have what we call a combo gate, which is a combination of both of those things. So that data is collected by that gateway, made available to both the cloud and the control system at the same time. So we're focused on vibration data for the purpose of this talk. Once that data goes through these gateways, it's going to hit those two locations, the cloud or the PLC. In the cloud case, that data migrates up to our web-based user interface we call the maintenance hub. It can be accessed via a public API. We also have the ability then to pull data from a PLC into that public API. To give a little bit more detail on our wireless vibration sensor, our legacy platform, which we call the VBT or vibration and temperature sensor, we have two versions of that, the 1 and the 2. These have triaxial accelerometers in them, as well as surface temperature sensors. They do all of that onboard vibration analysis we talked about. They give you roughly 30 meters line of sight wireless communication, and the difference between those two devices is the vibration bandwidth that they support. So many bearing or gearbox applications would benefit from the VBT2, whereas if you're just looking for overall vibration monitoring, you can go with the lower cost VBT1. We do have a new device that's coming out probably early Q3. We call it our VBTX. This is a longer life battery that's included in this. We hope to get about 10 years of battery life instead of the 3 to 5 we get on our current platform. It has a longer RF communication range, up to 1,000 meters. We do include an internal shaft speed detector via a magnetic flux sensor. We include a couple of additional analysis techniques for defect classification purposes, and we are hoping to, well, we're not hoping to, this will be deployed with a hazardous location rating to allow for Class 1 Div 1 applications. One of the other kind of neat things that I'll point out here is coming later in the year will be our thermally powered wireless sensor, which will eliminate the need for batteries entirely. So this will draw from a hot surface and use the thermal gradient to power the vibration sensor in all of the things that it does. All right, from there, that data hits what we call our maintenance hub. This is where we provide a vibration analysis overview to the end user. We really try to present data like a vibration analyst would, but we do it on an hourly basis, not the typical monthly or quarterly schedule. We use this ecosystem to tie alarms and alerts to physical assets, not to individual sensors. And we do provide kind of easy to decipher banded vibration plots like you see here. Now that drives us into our defect classification portfolio. This is additionally coming soon. It will be launched with our new vibration sensor in early Q3. And the defect classification suite, its job is to be able to take that vibration analysis data and give an estimation of the likely defects that might be occurring that are causing elevations in vibration data that are being captured. And this is an example of kind of what that output looks like. The last thing, I think it's the last thing that I want to talk about with respect to our vibration platform is how easy it is to implement inside an industrial control system. So we have a variety of different ways that you can integrate our IoT technologies with your control system. Primarily we do that over an industrial protocol, either Ethernet IP or Modbus TCP IP. In the Ethernet IP case, we do have an add-on profile available for Rockwell Studio 5000, which makes it super easy to get vibration data that you're capturing from our wireless sensors, both up into our cloud, but also into your control ecosystem. So with that sets the stage now for kind of the last part of this talk, which is where I'll really drive into how artificial intelligence can layer on top of this ecosystem that's been created of vibration monitoring and Internet of Things driven data collection in order to really bring transformative value to the predictive maintenance community, right? So we just talked about how the industrial Internet of Things can enable the affordable collection of just a ton of industrial vibration data, right? Very low cost, easy to install, wireless vibration sensor on every asset in your facility gives you just a ton of information, right? So as a result of this, we can start to pull on AI to do some really interesting things with those data streams that are being collected. First and foremost, we can use predictive AI techniques to enable a true transition from condition-based monitoring to predictive maintenance. I'll talk about this in great deal later, but the idea is condition-based monitoring, right? It's assessing a threshold. The sensor hits the threshold and we alarm. The idea behind predictive monitoring is we're using an AI-driven model to look at the data trend and predict when it's going to hit that threshold, right? So it's going to give you earlier indication of problems. We can also pull on AI, specifically generative AI, to make vibration analysis and really the recommended industrial maintenance activities, make them accessible to somebody who's not necessarily trained in the maintenance field. And I'll talk a little bit about how we can do that later as well. But when I talk about generative AI, we're talking things like ChatGPT. And lastly, I think there's a trend towards using explainable AI on top of these other artificial intelligence paradigms to help maintenance teams trust the predictions or the classifications or the advice that's coming from their machine learning or artificial intelligence systems. And that's what we'll focus on for the rest of this talk. So when we talk about AI enhanced predictive maintenance, here's an example of one place in which predictive analytics can come into play. This is some work that I've done in the past with Iowa State University through our kind of subsidiary Perceive. And what we built in this case was a deep learning tool that would allow us to classify the type of bearing damage using a vibration signal. So if you have a bearing like the one you're seeing here, a rolling element bearing, there are some physics that define the output that we expect from this particular device as it becomes damaged. And what we did in this particular set of research is we built a physics-inspired convolutional neural network to drive a classification of the health of the system. So we would either classify it as healthy, or we'd point out one of these various faults that the particular bearing could have. I'm not going to get into any of the technical detail in this presentation, but really, at the end of this, the results are that with a high degree of accuracy, this vibration-based approach can not only tell you, hey, you got a problem, but I can tell you exactly what type of problem you have in your particular asset. So this isn't truly predictive still, right? This is a condition-based monitoring approach, but it's AI-driven. Second example here is where we start talking about prediction itself. So this is leveraging machine learning and artificial intelligence to drive probabilistic remaining useful life prediction. Again, it's a deep learning based approach with my partners at Iowa State through our Perceive entity, where we built a kind of two-stage model that would allow us to both classify and then predict the remaining useful life of a given asset. So again, if I've got a damage threshold and I want to maintain that threshold I want to maintain that asset before data reaches that threshold, the output from this particular approach is to give you a probability and a time span over which that particular asset might hit that threshold. And when we play it out, this is kind of what those results could look like. This comes from one of the papers we published on this. So here's that maintenance threshold I talked about. In this case, we've overly simplified. We've got an overall vibration level, a vibration level that's kind of the low end vibration we talked about, that's close to the shaft speed, and then we've got the bearing band, which runs typically from like 3.2 to 13.2 times the shaft speed. Okay, so if we look at these three data plots, that vertical line is the current point in time, and then everything from there out is the projection of when that particular asset is going to reach a critical point based on these maintenance thresholds. So you can see from this top plot that we expect that this particular asset is going to hit an issue that requires maintenance in the next 45 to 60 days, right? You can kind of see a probability distribution based on that ensemble of predictions that we're showing here. The other thing that we can see from these three plots is that we don't expect that this has anything to do with alignment or balance, because we're not predicting any sort of major increase in the low frequency component of this signal, right? Despite we've seen some perturbation there, we're not actually predicting an exceedance of that threshold anytime in the near future. On the flip side, we are predicting in a timeline that aligns with our overall expectations that the bearing band specifically is going to hit a problematic spot in the next 45 to 60 days. So we're able to probabilistically provide a remaining useful life prediction that says, hey, maintenance team, there's a high degree of likelihood that this bearing is going to require replacement in the next 45 to 60 days. So that from a predictive maintenance perspective drives me into one more kind of example here. This is really drawing from the generative AI side of the artificial intelligence equation. And what we've done here, again, through the Perceive entity, is build an artificially intelligent chatbot that can be used to provide maintenance advice to technicians or maintenance personnel who may not have training in how to resolve an issue that's occurring in their maintenance purview, right? So we provide AI-assisted insights into identified problems. So that's if data starts to indicate a certain problem, we can add context to that in terms of the AI's understanding of that problem and give it in a conversational way. We can increase certainty in the failure detections that the AI is making. So if our prediction says there's going to be a bearing problem in 45 to 60 days, this Foreman XAI technology can come alongside the maintenance team and say, I can add to your certainty that problem is going to happen if you perform these steps. Once it's determined that, yeah, we do need to fix this bearing, but I don't know how, we do have the capability within this technology to bring in documentation, things like installation guides or technical resources for the asset that is experiencing the defect. and give recommendations for how to fix the detected issues before they become a problem. And then last and not least, this generative platform will allow for root cause analysis to hopefully assist the maintenance team in preventing these sort of defects from happening in the future if such prevention is possible. All right, so I think this is my last example here, and then we'll talk a little bit about explainability. This takes the work that we did in bearing classification, and it embeds that capability inside an industrial Internet of Things device. Okay, so I probably said a lot there, but earlier we talked about how we could build a model that could detect whether a problem was, or whether a bearing was healthy or experiencing any one of a number of different types of degradation, from outer race failure to inner race failure to ball path, a ball problem, etc. What we did in this particular work was we took that model that we developed and trained, and we embedded it within our wireless sensing platform. So the idea being that instead of sending the raw data to some computer or computing resource, whether it's in the cloud or locally, that could do that investigation and run those machine learning AI ML models, we actually embedded that inside the sensor device itself, so that all that sensor does is it sits on that bearing and it says, I'm healthy, or I have this problem or that problem or the other problem. And by doing that, we further decrease the amount of information that needs to be transmitted from that wireless device, which ultimately reduces the amount of power required. It lengthens the battery life, gives us more wireless bandwidth to deal with, has all of those benefits. So again, all of this kind of came out of the academic relationships we have through our subsidiary Perceive and Iowa State. So with this kind of as a background for some just quick examples of how we've been leveraging this technology in our sphere, let's talk about what's preventing the widespread adoption of AI in the predictive maintenance space. And we are starting to see some of that adoption, but it's still not as widespread as I would expect given the potential advantages to the community. The biggest hurdle, honestly, is probably implementation costs, right? Those are coming down, but generally it's tough to look at an artificial intelligence and justify a huge spend on that right up front. I'm not going to talk about that today, but that is an impediment. Integrating AI ML technologies into existing industrial ecosystems is tough. We're typically in the industrial space not designed for cutting edge things, and this is one example of that. So again, not the focus of the rest of this presentation, but definitely a challenge. One of the biggest challenges we face in the predictive maintenance space as we talk about AI technologies is how do we grab quality data and then control it in a way that enables AI or ML techniques to do what they do well. And that's a massive hurdle that's going to have to be addressed in coming years. I'm sure we're all aware of the cybersecurity ramifications of doing anything that potentially ties to the cloud. And as we kind of leverage and start to use AI-based techniques more and more, we're going to see increasing concerns surrounding cybersecurity and data privacy. But what I really want to talk about with just the last few minutes of this presentation is how explainability and trustworthiness of machine learning or artificial intelligence systems is being overcome in a way that will enable true trustworthiness of machine learning or artificial intelligence in the predictive maintenance space. All right, so when we talk about explainability, there's several main challenges that we're trying to overcome. First one is that AI models, specifically when we're dealing with deep learning, which I know I didn't talk about much today, but just in general, these models are very complex. And they're difficult to interpret even for the humans that work on them. They may not have any context in reality. It's also challenging that highly accurate models. So the better the model is at predicting or classifying something, oftentimes it's less interpretable or less explainable. So the better it is at doing what it's doing, the more abstract it is in terms of its contents, the way it's been created. And as a result, it's hard to know exactly why it's predicting the thing it's predicting, even though it seems to be doing so accurately. And kind of the last challenge here in the explainability space is that certain industries I haven't seen this in predictive maintenance yet, but certain industries are starting to lay regulations down requiring explainability. So in other words, as AI is predicting or classifying things for us, it's a requirement from a regulatory body that the AI explains its work, basically justifies why it's giving the prediction it's giving. And obviously that has greater play in the financial sector. If you have an AI that's trying to approve or deny a loan application, you don't want it to discriminate based on some factor that's not allowed, right? And we need to understand why that type of AI is making the decisions it's making. However, right, if we can get to the point in the industrial predictive maintenance world where AI is truly explainable, users, which usually are maintenance technicians or maintenance managers, if we can get to the point where they understand how the AI model is working, they're almost 100% more likely to trust and use that model, right? The higher level of trust we can drive, the more utilization we can get out of the benefits that AI can bring. It also, as we drive trust and understanding in our models, that's going to help us use the previous behavior of those models to build and improve the design and performance of AI models moving forward, right? So the more explainable things are, the easier it is to incrementally develop them in a positive way. And lastly, and again, I haven't seen this in the predictive maintenance space, so I don't know that it applies here, but in industries where those explainability requirements start popping up, explainable AI can help meet those regulatory demands. All right, so what do I mean when I say explainable AI? What I'm talking about is building methods or strategies that sit on top of artificial intelligence in order to help that AI be understood by human experts. This contrasts with what we typically see when we have an artificial intelligence as a black box where the AI is making some decision that humans can't interpret. Right? If I go into ChatGPT or another kind of generative AI text-based interface and ask a question, it'll give me an answer, and I have no idea why it's giving me the answer it's giving. It's been trained, on a huge corpus of data to give that answer. It probably can't even fully explain, where that answer came from. And in some cases, including predictive maintenance, that can be problematic. So if we start to implement explainable AI technologies, that's going to allow operators and decision makers in the industrial space to better understand the AI-driven outcomes that they're using to drive their decision making, right? So understanding the AI helper is going to help make better decisions. It's also going to help us verify the soundness of our model, right? If the logic that the AI gives behind why it's predicting something makes sense to a human, that's going to help us verify that the model is doing what we expect it to do. It also will help align a predictive model with intuition that a technician has from working with industrial equipment for however many years, right? And it builds trust because it mirrors the way a human would go about making decisions in that same capacity. And lastly, I think insights derived from artificially intelligent models that are explainable can obviously be more effectively communicated with anybody. Put yourself in the seat of like a doctor who's grabbing information about a patient from an AI system. If he can't explain why the AI is saying what it's saying, right? It's just saying, hey, you need this surgery. That patient is not likely to be super confident that result is accurate, that prediction or whatever the advice is accurate coming from the AI assistant. Whereas if the doctor can explain with human-based rationale why that surgery is being recommended by the AI, then it's just a backup to help reinforce a decision that's being made by a collaboration between a human expert and an AI-based system. So speaking of that doctor kind of medical example, this is one of the main, papers that we've used internally to help drive our thinking around how to deploy explainable artificial intelligence in the predictive maintenance space. This is an example from the Journal of Nature Biomedical Engineering, where a group of researchers were looking to detect, using an AI system, hemorrhaging of different types, right? So they're first detecting a hemorrhage, and then they're classifying what type of hemorrhage that is. I'm not going to drive into too much detail here, but this top plot is visualizing the probability that a given image that they've taken from a brain scan is subject to a certain type of hemorrhage, right? So you see here, and I don't know the actual names from the medical perspective, but there's a red hemorrhage and a blue hemorrhage. Probably not the technical terms. And you can see that there are different cases in which the probability of those two issues is higher, right? We're then from the system going to allow the medical personnel who's interfacing with this to visualize the location of the hemorrhage within the brain scan that's been taken. And then the last thing that's going to happen, actually, I think there's two more things. So it's going to visualize what we call the activation map. So it's pointing out the portions of these brain scan that are most impactful, like the location in that image that shows the most impactful things that are leading the AI to determine that is a blue or a red hemorrhage. Then the last thing it's going to do is it's going to give a set of images from previous experience that it is using to reinforce its conclusions that this is, in this case, a blue hemorrhage, right? So it's going to pull up, any number of previous brain scans from other patients that we know are blue hemorrhages and allow the doctor to look at those and validate in their own mind that these training samples of blue hemorrhages match the situation that they're seeing in reality. Okay, so how do we deploy that? This, I think, is my last slide here as we wrap up. How do we deploy that to do bearing specific defect classification, right? So we're talking about bearings here because it's easy in the academic sense, but this could be deployed on any issue driving out of vibration-based monitoring. Okay, what we do here is very much the same thing as what you see in the hemorrhage example, right? We're going to take data from a vibration sensor. The AI is going to say, I believe that this, with this degree of certainty, is an inter-race bearing fault, right? And what's going to happen from there is the AI is then going to present that as a probabilistic, I have a 70% certainty that this is the issue. And it's going to say, I believe that this is the issue because of these frequency components. And you can see here on the left, it's highlighting portions of the frequency spectrum that it deems most relevant to the classification that it's giving. And this aligns with what we talked about earlier in the vibration spectra. There are certain frequencies related to certain faults, and that's what it's doing here. Then it's going to also pull from its set of training data. These are examples before where it has seen failure of the same type, and it's going to say, look, these failure trends look very, very similar to the one that I'm seeing, and coupled with the physics-based intuition I have in this plot in the bottom left, these are examples that helped me make this decision, right? And those are the types of imagery that can be provided to a maintenance technician who's trying to decide whether to replace that bearing based on this AI's advice to make a better, more informed decision. So I do want to point out this particular work is being done with the University of Connecticut in collaboration with our subsidiary Perceive. So that brings me to the end of the conversation here. This was there was a lot of content there. I'm sure there's a lot of questions. I'd love to kind of take those either in person here or offline. I appreciate your time.